I'm going to start with talking about the significance of technological advances. There are a lot of things that matter for certain purposes about the understanding of the technology, and that's really what I'm going to talk about. To begin with, I have to make a couple of distinctions because you won't really understand contemporary intellectual life if you don't understand these distinctions. In our culture, there's a big deal about objectivity and subjectivity. We strive for an objective science. The problem is that these notions are systematically ambiguous in a way that produces intellectual catastrophes. They're ambiguous between a sense which is epistemic, where epistemic means having to do with knowledge, epistemic, and a sense which is ontological, where ontological means having to do with existence. Now, the problem with objectivity and subjectivity is that they're systematically ambiguous between an epistemic sense, I'll just abbreviate subjectivity, between an epistemic sense and an ontological sense. Epistemically, the distinction is between types of knowledge claims. If I say Rembrandt was born in 1606, that is to say is a matter of objective fact. That's epistemically objective. But if I say Rembrandt is the greatest painter that ever lived, well, that's a matter of opinion. That is epistemically subjective. Okay? So you have epistemic objectivity and subjectivity. Underlying that is a distinction in modes of existence. Lots of things exist regardless of what anybody thinks. Mountains, molecules, and tectonic plates have a mode of existence that's ontologically objective. But pains and tickles and itches, they only exist insofar as they are experienced by a subject. They are ontologically subjective. So I want everybody to get that distinction because it's very important because, well, for a lot of reasons, but one is lots of phenomena that are ontologically subjective admit of an account which is epistemically objective. I first got interested in this kind of stuff. I thought, well, why don't these brain guys solve the problem of consciousness? And I went over to UCSF to their neurobiology gang and told them, why the hell don't you guys figure out how the brain causes consciousness? What am I paying you to do? And their reaction was, look, we're doing science. Science is objective, and you yourself admit that consciousness is subjective. So there can't be a science of consciousness. Now you'll all recognize that's a fallacy of ambiguity. Science is indeed epistemically objective because we strive for claims that can be established as true or false independent of the attitudes of the makers and interpreters of the claim. But epistemic objectivity of the theory does not preclude an epistemically objective account of a domain that's ontologically subjective. The point is this: you can have an epistemically objective science of consciousness even though consciousness is ontologically subjective. Now that's going to be important. There's another distinction which is crucial, and that's between phenomena that are observer independent, and there I'm thinking of mountains and molecules and tectonic plates. They exist regardless of what anybody thinks. But the world is full of stuff that matters to us that is observer relative. It only exists relative to observers and users. So for example, the piece of paper in my wallet is money. But the fact that makes it money is not a fact of its chemistry. It's a fact about the attitudes that we have toward it. So money is observer relative. Mountains, money, property, government, marriage, universities, Google, cocktail parties, and summer vacations are all observer relative. And that has to be distinguished from observer independent. And notice now, all observer relative phenomena are created by human consciousness. Hence, they contain an element of ontological subjectivity. But you already know that you can have in some cases, an epistemically objective science of a domain that is observer relative. That's why you can have an objective science of economics, even though the phenomena studied by economics is in general observer relative and hence contains an element of ontological subjectivity. Economists tend to forget that. They tend to think that economics is kind of like physics, only it's harder. It's not. You know, when I studied economics, I was appalled. We learned that marginal cost equals marginal revenue in the same tone of voice that in physics we learned that force equals mass times acceleration. They're totally different because the stuff in economics is all observer relative and contains an element of ontological subjectivity. And when the subjectivity changes, the whole thing collapses. That was discovered in 2008. Okay, this is not a lecture about economics. I want you to keep all that in mind. Now that's important because a lot of the phenomena that are studied in cognitive science, particularly phenomena of intelligence, cognition, memory, thought, perception, and all the rest of it, have two different senses. They have one sense which is observer independent, and another sense which is observer relative, and consequently we have to be very careful that we don't confuse those senses, because many of the crucial concepts in cognitive science have as their reference phenomena that are observer relative and not observer independent. I'm going to get to that. Now I'm going to go and talk about some intellectual history. Many years ago, before any of you were born, a new discipline was born. It was called cognitive science. And it was founded by a whole bunch of us who got sick of behaviorism and psychology, effectively. That was the reason for it. And the Sloan Foundation used to fly us around to lecture, mostly to each other. But anyway, that's all right. We were called Sloan Rangers, and I was invited to lecture to the Artificial Intelligence Lab at Yale. And I thought, well, Christ, I don't know anything about artificial intelligence. So I went out and bought a book written by the guys at Yale. And I remember thinking, $16.95 plus tax, money wasted. Well, it turned out I was wrong. They had in there a theory about how computers could understand. And the idea was that you give the computer a story, and then you ask the computer questions about the story, and the computer would give the correct answer to the questions, even though the answer was not contained in the story. A typical story. Guy goes into a restaurant and orders a hamburger. When they brought him the hamburger, it was burned to a crisp. The guy stormed out of the restaurant and didn't even pay his bill. Question, did the guy eat the hamburger? Well, all of you computers know the answer to that. No, the guy didn't eat the hamburger. The point was, this proves that the computer really understands the story. The program is purely syntactical. It is defined entirely as a set of operations over syntactical elements. To put it slightly more technically, the notion same implemented program defines an equivalence class that is specified completely independently of any physics, and in particular independent of the physics of its realization. Computers are purely syntactical devices. Their operations are defined syntactically, and human intelligence requires more than syntax. It requires a semantics. It requires an understanding of what's going on. Okay, so the bottom line is that the implemented computer program by itself is never going to be sufficient for human understanding, because human understanding has more than syntax. It has a semantics. Syntax is not semantics, and simulation is not duplication. You can simulate. The bottom line is there's a logical truth, and that is that the implemented computer program is defined syntactically, and that's not a weakness. That's the power. The power of the syntactical definition of computation is you can implement it on electronic machines that can perform literally millions of computations in a very small amount of time. Now, another argument I sometimes got was, well, in AI programs, we often have a section called the semantics of natural understanding programs, and that's right. But of course, what they do is they put in more computer implementation. They put in more syntax. A lot of people thought, well, look, maybe the computer doesn't understand, but all the same, it does information processing. And it does, after all, do computation. That's what we defined the machine to do. And I had to review a couple of books recently. One book said that we live in a new age, the age of information. And in a wonderful outburst, the author said, everything is information. And I read another book. This was an optimistic book. I reviewed, this was for the New York Review of Books, a less optimistic book by a guy who said, computers are now so smart, they're almost as smart as we are, and pretty soon they'll be just as smart as we are. And then I don't have to tell this audience the next step, they'll be much smarter than we are. And then look out, because they might get sick of being oppressed by us, and they might simply rise up and overthrow us all. And this, the author said modestly, I guess it's how you sell books, he said, this may be the greatest challenge that humanity has ever faced, the upcoming revolt of super smart computers. Okay, now I want to say both of these claims are silly. I mean, I'm speaking shorthand here. The notion of intelligence has two different senses. It has an observer-independent sense, where it identifies something that is psychologically real. So I am more intelligent than my dog Tarski. Now Tarski's pretty smart, I agree. But overall, I'm smarter than Tarski. Now he's very smart, but he does have intelligence in the same sense that I do, only he happens to have somewhat less than I do. Now my computer is also intelligent, and it also processes information, but, and this is the key point, it's observer relative. The only sense in which the computer has intelligence is not an intrinsic, but it's an observer relative sense. We can interpret its operations in such a way that we can make, now watch this terminology, we can make epistemically objective claims of intelligence, even though the intelligence in question is entirely in the eye of the beholder. This was brought home forcefully to me when I read in the newspapers that IBM had designed a computer program which could beat the world's leading chess player. And in the same sense in which Kasparov beat Karpov, so we were told Deep Blue beat Kasparov. Now that ought to worry us, because for Karpov and Kasparov to play chess, they both have to be conscious that they're playing chess. They both have to know such things as, I opened with pawn to king 4, and my queen is threatened on the left-hand side of the board. But now notice, Deep Blue knows none of that because it doesn't know anything. You can make epistemically objective claims about Deep Blue. It made such and such a move. But the attributions of intelligence, chess playing, this move or that move, it's all observer relative. None of it is intrinsic. In the intrinsic sense in which I have more intelligence than my dog, my computer has zero intelligence, absolutely none at all. It's a very complex electronic circuit that we have designed to behave as if it were thinking, as if it were intelligent, but in the strict sense, in the observer-independent sense in which you and I have intelligence, there is zero intelligence in the computer. It's all observer relative. And what goes for intelligence goes for all of the key notions in cognitive science. The notions of intelligence, memory, perception, decision-making, rationality, all those have two different senses. A sense where they identify psychologically real phenomena of the sort that goes on in you and me, and the sort where they identify observer-relative phenomena, but in the intrinsic sense in which you and I have intelligence, the machinery we're talking about has zero intelligence. It's no question of its having more or less. It's not in the same line of business. All of the intelligence is in the eye of the beholder. It's all observer relative. Now notice, mental processes by which we attribute intelligence to the computer require consciousness. So the attribution of observer relativity is done by conscious agents, but the consciousness is not itself observer relative. The consciousness that creates the observer relative phenomena is not itself observer relative. Okay, but now let's get to the crunch line then. If information is systematically ambiguous between an intrinsic sense, in which you and I have information, and an observer relative sense, in which the computer has information, what about computation? After all, computation, that must surely be intrinsic to the computer. That's what we designed and built the damn things to do, was computation. But of course, the same distinction applies. When I first read Alan Turing's article, it was called Computing Machinery and Intelligence. Now, why didn't he call it computers and intelligence? Well, you all know the answer. In those days, computer meant person who computes. A computer is like a runner or a piano player. It's some human who does the operation. Nowadays, nobody would think that because the word has changed its meaning, or rather it's acquired this systematic ambiguity between the observer relative sense and the observer independent sense. Now we think that a computer names a type of machinery, not a human being who actually carries out computation. But the same distinction that we've been applying, the same distinction that we discovered in all these other cases, that applies to computation. In the literal or observer independent sense, in which I will now do a simple computation, I will do a computation using the addition function, and here's how it goes. It's not a very big deal. 1 plus 1 equals 2. Now, the sense in which I carried out a computation is absolutely intrinsic and observer independent. I don't care what anybody says about me. If the experts say, well, you weren't really computing. No, I was. I consciously did a computation. When my pocket calculator does the same operation, the operation is entirely observer relative. Intrinsically, all that goes on is a set of electronic state transitions that we have designed so that we can interpret computationally. And again, to repeat, for most purposes, it doesn't matter. When it matters is when people say, well, we've created this race of mechanical intelligences, and they might rise up and overthrow us, or they attribute some other equally implausible psychological interpretation to the machinery. In commercial computers, the computation is observer relative. Now notice, you all know, that doesn't mean it's epistemically subjective. And I pay a lot of money so that Apple will make a piece of machinery that will implement programs that my earlier computers were not intelligent enough to implement. Notice the observer relative attribution of intelligence here. So it's absolutely harmless unless you think there's some psychological significance. Now, what is lacking, of course, in the machinery which we have in human beings, which makes the difference between the observer relativity of the computation in the commercial computer and the intrinsic or observer independent computation that I have just performed on the blackboard, what's lacking is consciousness. All observer relative phenomena are created by human and animal consciousness, but the human and animal consciousness that creates them is not itself observer relative. So there's an intrinsic mental phenomenon, the consciousness of the agent, which creates the observer relative phenomena or interprets the mechanical system in an observer relative fashion. But the consciousness that creates observer relativity is not itself observer relative. It's intrinsic. What is the difference between the computer and the brain? In one sentence, the brain is a causal mechanism that produces consciousness by a certain rather complex and still imperfectly understood neurobiological processes. But those are quite specific to a certain electrochemistry. We just don't know the details, but we do know if you mess around in the synaptic cleft, you're going to get weird effects. How does cocaine work? Well, it isn't because it's got a peculiar computational capacity. It's because it messes with the capacity of the postsynaptic receptors to reabsorb quite specific neurotransmitters, norepinephrine. What are the other two? God, I'm flunking the exam here. Dopamine is what, GABA is the third. Anyway, the brain, like the stomach or any other organ, is a specific causal mechanism. And it functions on specific biochemical principles. The problem with the computer is it has nothing to do with the specifics of the implementation. Any implementation will do, provided it's sufficient to carry out the steps in the program. Programs are purely formal or syntactical. The brain is not. The brain is a specific biological organ that operates on specific principles, and to create a conscious machine, we've got to know how to duplicate the causal powers of those principles. Now, the computer doesn't in that way work as a causal mechanism producing higher level features. Rather, computation names an abstract mathematical process that we have found ways to implement in specific hardwares. But the hardware is not essential to the computation. Any system that can carry out the computation will be equivalent.